simplify, recall that if I have y is equal to log of x with the base b, if I don't have any number for the base, is assumed to be 10. To solve for x here, I need to write this in terms of its exponential form. So that would be b to the power of y is equal to x. You notice that the base of the logarithm and base of exponential matching. So that's what we need to do here. I need to write this in terms of its exponential so I can solve for x. My base here is 2, so I'm going to start with that. It would be 2 to the power of 54 is equal to x. That's my argument, they call it. And this is it. X is equal to 2 to the power of 54. We can leave the answer just like that, or we can just use your calculator and raise 2 to the power of 54, but this is just fine. Simplify. We need to convert this to its exponential form. If I have y is equal to log of x with the base b, that would be the same as b to the power of y is equal to my argument x. So in this case, I have 2 to the power of x is equal to my argument would be 32. When you get to this point, if I can make the base the same, then I can conclude from there the exponents would be the same. Looks like I can write 32 as 2 to the power of 5. So 2 to the power of x would be equal to 2 to the power of 5. If the base are the same, then the exponents must be the same. If I have a to the power of n is equal to a to the power of m, I can conclude from here that n must be the same as m. So x must be equal to 5 here. Here we're going to simplify. I need to rewrite this as its exponential form. If y is equal to log of x with the base b, I can write this as b to the power of y is equal to x. My argument is x. So here I would write this as x to the power of 2, my base is x, is equal to my argument, which is 121. So in this case, I need to just simply solve for x. I can take a square root of both sides. So x would be equal to plus and minus square root of 121, which is equal to plus and minus 11. So I get two answers here. X is equal to 11 or x is equal to negative 11. I cannot accept the negative number, so x would be only equal to 11. Here we want to simplify. If you recall, if I have a to the power of n is equal to a to the power of m, we can conclude from here that n is equal to m. So in this case, if I can make the base the same, I can conclude that the exponents would be the same. Here I have 2 to the power of x is equal to 8. I can write 8 as 2 to the power of 3. So from here I can conclude that x would be equal to 3. Here we want to simplify. Let's take a look at the properties that we had before. If I have natural log of e to the power of x, the base for natural log is e. When the base is matching the base of your argument, then the whole thing would be equal to x. It's also true for log. If I have log of b to the power of x, if the base of the logarithm matches the base of these exponents, this whole thing would be equal to x. These are the two properties you need to know. So in this case, they're asking you to what's natural log of e to the power of 100. So we know the base of natural log of e. According to this property, this whole thing would be equal to just 100. Here simplifying, log of 5 with the base is 125. So I can write this as equal to, let's say, x. Recall, if I have y is equal to log of x with the base b, I can write this as b to the power of y is equal to x. So in this case, I can write this as 125, that's my base, to the power of x is equal to my argument 5. If I can make the base the same, I can conclude that my exponents would be the same. So if I have a to the power of n is equal to a to the power of m, I can conclude from here that n must be equal to m. Looks like I can make the base the same in this case. So I can write 125 as 5 to the power of 3. So let's replace 125 to 5 to the power of 3, and then I have this x here equal to 5. So this will be like 5 to the power of 1. So when the base are the same, the exponents must be the same. So 3x must be equal to 1. You can solve for x. Divide both sides by 3. So x would be equal to 1 over 3. Here we want to simplify. We can recall if I have log of b to the power of x with the base b, this whole thing would be equal to just x. So in this case, we have log of 4 to the power of 5 is matching the base. So this whole thing must be equal to just 5. Here we're going to simplify. We have 7 log of 81 with the base 9. If you remember, if I have log of b to the power of x with the base being b, this is equal to x. Now the question is, can I make 81 and 9 to have the same base? 81 is equal to 9 to the power of 2. So if I replace 81 with 9 to the power of 2, you can see now we are looking at this property right now. This b and this b matching. So this portion would be just equal to 2. So I can write log of 9 to the power of 2 with the base being 9 must be equal to 2 then. So this would be just simply 2. And then we have 7 here. We need to multiply that together. It would be 14. So log of 81 with the base 9 times 7 would be equal to 14. Here we want to solve for x, and we have log of base 2. My argument here is log of 49 with the base 7, and you want to solve for x here. So let's go ahead and evaluate what is the argument is equal to. For that, I'm going to recall the property that I learned before. Log of b to the power of x with the base being equal to b, that would be the same as x. I can write 49 as 7 to the power of 2, right? 7 times 7 would be 49. And as you can see, the base here is 7. So I have log of 7 squared. That is really the same as log of 49 with the base 7. I write it as 7 squared so I can match these two numbers. So this whole thing must be equal to 2 according to this property right above it. So really what we're looking at is log of 2, this is just 2, with the base 2 is equal to x. That's what we're looking at. In order to solve for this, I can write this as its exponential function. If you remember, if I have y is equal to log of x with the base b, I can write this as b to the power of y is equal to x. So I'm going to write this as its exponential function. So this would be 2 to the power of x is equal to the argument being 2. The base are already the same. If I have a to the power of n is equal to a to the power of m, I can conclude from here that n must be equal to m. So therefore, x must be equal to just 1 here. Here we'll solve for x. We have log of x is equal to minus 2, and the base is 1 over 5. So I have y is equal to log of x with the base b. I can write this as its exponential function would be b to the power of y is equal to the argument x. So in this case, my base is 1 over 5. So I can write this as 1 over 5 to the power of minus 2, which is equal to my argument, which is x. Remember, if I have a over b to the power of minus n, that's the same as b over a to the power of plus n. So I can write this as 5 over 1 to the power of plus 2. That's what x is. So x is equal to 5 squared, which is equal to 25. X equal to 25. Here you want to find x. You have 2 to the power of 2x plus 3 is equal to 32. If I can make the base the same, I can conclude that the exponents are the same. A to the power of n is equal to a to the power of m. If a to the power of n is equal to a to the power of m, I can conclude from here that n must be equal to m. And it looks like I can write 32 as 2 to the power of 5. So 2 to the power of 2x plus 3 is equal to 2 to the power of 5. The bases are the same, therefore the exponents must be the same. 2x plus 3 must be equal to 5, and I would solve for x here. 2x is equal to 5 minus 3. 2x is equal to 2. Divide both sides by 2. X would be equal to 1. Write each exponential form in logarithmic form. If I have y is equal to log of x with the base b, I can write this as b to the power of y is equal to my argument x. I can write this back and forth. If I have my expression in terms of logarithm, I can change it to exponential. If I have it in terms of exponential, I can write it in terms of a logarithm. So in this case, I have 5 to the power of 3 is equal to 125. I have it in terms of exponentials here. So I'm going to write it in terms of the logarithm. So I will write this as log of 125 is equal to 3, and the base would be 5. Notice that the base of the logarithm matching the base of the exponential. So 5 to the power of 3 is equal to 125. 125 is my argument, which would be always to the right of the equal sign. We want to write exponential form in logarithmic form. Recall y is equal to log of x with the base b. That is the same as b to the power of y is equal to x. So here I have 1/8, that's my base, to the power of minus 2 is equal to 64. So I'm going to write this as log of, I know what my base is, right? I'm going to write that down, it's 1/8 here. My argument is the number to the right of the equal sign, which is 64, must be equal to -2. Write exponential form in logarithmic form. Recall, if I have y is equal to log of x with the base b, that's the same as b to the power of y is equal to x. So I'm going to write a to the power of b is equal to c as log of, I'm going to start with my base. My base should match the base of the exponential, which is a. My argument is the number to the right of equal sign, which is c, is equal to b. Write each logarithmic form in exponential form. Recall, when y is equal to log of x with the base b, that would be the same as b to the power of y is equal to x. So in this case, I would write 2 to the power of 6 is equal to my argument 64. And that should make sense. 2 to the power of 6 is equal to 64. We want to write natural log of m is equal to n as is exponential form. If I have y is equal to natural log of x, the base would be e. You don't write it down, but it's always e. Is a fixed number. That would be e to the power of y is equal to x. Now compare this with log. Y is equal to log of x with the base b. Similar relationship. B to the power of y is equal to x. So when I have natural log of m is equal to n, the base is e. So it would be e to the power of n is equal to m. Here we want to write log of 0.01 is equal to -2 as exponential form. If I have log of x with the base b is equal to y, I can write this as exponential form as b to the power of y is equal to x. So in this case, I have log of, my argument is 0.01 equal to -2. When there's no number here, it means the base is 10. So it would be 10 to the power of -2 is equal to my argument, which is 0.01. And that is true. 10 to the power -2 would be 1 over 10 to the power +2, which is equal to 0.01. We want to use the properties of the logs to rewrite each expression as a single logarithm with coefficient 1. For that, I'm going to recall some properties. If I have log of x times y, my argument is a product of two terms. I would write this as log of x plus log of y. That's how you expand them. You notice that I didn't write the base here. If I don't write the base, it means the base is 10. Just to make this relationship simple, I'm just going to ignore the base for now. But if the base was different, we just have to match the whatever base we have here. Next one, if I have log of x over y, if my argument is the quotient, then I could write this as log of x minus log of y. And next one, if I have log of x to the power of n, I can write this n and move it right front of the log. That would be the same as n log of x. In other words, if my argument is product, quotient, or power of something, I can expand them. You notice that the base must be the same. So I didn't write the base to just make it a little simple to look at, but now I can put all the base here as being the same. If I don't write anything, it means it's 10. So I'm going to make all the base equal to b here. So these are the three properties that we need to know. So in this case, if I want to write this as a single logarithm, this 100 can be right on the exponents here. So here what we have, n times log of x is the same as log of x to the power of n. In other words, I can move this n and put it right over here. That's what we're doing. Moving this n, put it right over here. So in this case, I can do the same thing here. I can move this 100 and make that my exponents. That would be 100 right here. Plus, I do the same thing with 5. That would be the same as log of x minus 1 to the power of 5. Minus. And write the last one as log of z plus 5 to the power of 3. Now, if I combine these two, this would be the sum of 2 log. I can write it as the product. That would be the log of 2x plus 31 to the power of 100 times x minus 1 to the power of 5. Then write minus log of z plus 5 to the power of 3. So just combine the first two using the first property into the product. may want to put the brackets here. That's my argument now. So now, to combine these two, I'm going to use the second property and write this as a quotient. That would be log of, my first argument is 2x plus 31 to the power of 100 times x minus 1 to the power of 5. Now, because this is minus, would be over z plus 5 to the power of 3. So we combine that into a single logarithm. Here we want to use the properties of the logs to rewrite this expression as a single logarithm with coefficient of 1. Let's write down the list of the properties we need to know for this. Log of x times y, the argument is a product. Then I can write this as log of x plus log of y. If my argument is quotient, x over y, I can write this as log of x minus log of y. If I have log of x to the power of n, that's the same as n log of x. Again, all the base must be the same, so now I can copy all these as being base b. If not, we assume this is 10. Looks like that here I can move this 1 over 3 as the exponents. So let's do that one first. I have log of x plus y. We have minus log of x plus z to the power of 1/3. We're using the third property here, right here, this one. Log of x plus y, that would be the same as, here I have log of x plus y. You see my argument is a sum of x and y. And if you look at the property I have on the right-hand side, you said if the argument is a product, quotient, or power, I can expand it, not if it's sum. So I have to leave this as log of just x plus y. This is already in a single logarithm. However, this minus means you're going to change this into a single logarithm using the second property here. If this is log of x minus log of y, that would be log of x over y. So my x really here is x plus y. So it would be log of x plus y if I were going to combine this, over the second one is x plus z to the power of 1/3. See, I'm combining these two log into a single log, and notice that the base is b here. So go ahead and copy b here for all of these. Okay, I combine this into a single logarithm already. I can rewrite this as log of x plus y over, I can write this as cube root of x plus z would be 2z. We're writing this as a single logarithm, and the base is b here. Now the question is, how do I get cube root? So the property that we used to have, here when I have a to the power of n over m, that is the same as mth root of a to the power of n. So if I have a to the power of 1/3, this would be the third root of a to the power of 1. That's what we're using. We're going to use the properties of the logs to decompose the following logarithmic of the first degree polynomials. For this one, we need to recall some properties. When I have natural log of x times y, that is the same as natural log of x plus natural log of y, just like the log, same properties. If I have natural log of x over y, that would be the same as natural log of x minus natural log of y. So in this case, it looks like I have natural log of x over y. I have this one here. I will write that as natural log of x to the power of 5 minus natural log of cube root of x cubed minus 1. We are applying the second property here. To expand the first term, I'm going to go to the first property. If I have natural log of x times y, that would be the same as natural log of x plus natural log of y. So I'm going to write this as natural log of e plus natural log of x to the power of 5. Continue with writing as minus natural log of, I'm going to write this as x to the power of 3 minus 1 to the power of 1/3. Recall, if I have nth root of a to the power of m, that's the same as a to the power of m over n. You had one more property here. If I have natural log of x to the power of n, I can write this as n times natural log of x, just like the log. What is natural log of e? Recall, if I have natural log of e to the power of x, because the base is e, so this whole thing would be equal to x. Therefore, natural log of e is really natural log of e to the power of 1, and the base here is e, so this whole thing would be equal to that exponent 1. So this would be just 1. Next one, if I want to expand that one, I'm going to move the 5 right front of natural log of x, so it would be 5 natural log of x minus. Next one, I'm going to move the 1/3 front of natural log of x cubed minus 1. You notice that I cannot expand x cubed minus 1 because it's not product, quotient, or power of something. So pretty much you're going to look at the arguments, and if the arguments would be product, quotient, or power of something, we can expand it. If not, we're done. So it looks like that's as far as we can go with this one. We want to expand this log using the properties that we learned. Let's recall the properties. If I have log of x times y, my argument is the product of something, I can write it as log of x plus log of y. If my argument is a quotient, x over y, I can expand this as log of x minus log of y. If my argument is a power of something, x to the power of n, I can write this as n log of x. The base would be the same for all these. I'm going to put b for all of them. If not, it's 10. So in this example, I have log of x over y. This is what I'm going to start with. I'm going to write this as log of, my x would be all the terms at the top of the fraction, would be 10x times x plus 10 squared. Now minus log of what I have at the bottom of the fraction, which is 25 minus x to the power of 5. Looks like I can continue with expanding the first one because there are products. The product of 10 times x plus 10 squared. So I can write this as log of 10 plus log of x plus log of x plus 10 squared. That would be for the first part. Minus, here I can move the 5 right front of the log because that's all I have here is a power. That's log of x to the power of n. So it would be minus 5 log of, my argument would be 25 minus x. You notice 25 minus x is not product, quotient, or power, so I can not move ahead with expanding this part. Next one, log of 10. Recall, log of a to the power of n with the base a, that would be the same as n. So because the base here is just 10 and the exponent is 1, so log of 10 would be just 1 plus log of x plus, I'm going to move this 2 right in front of the log because here I have a power. So it would be 2 log of x plus 10 minus 5 log of 25 minus x. Just to check, make sure that we're done with this, we're going to look at the arguments for each of these and make sure the arguments is not product, quotient, or power of something. X is not. X plus 10 is not the product, quotient, or power of anything. 25 minus x is not product, quotient, or power or anything, so we can leave it alone. And that's as far as we can get with expanding this. Graph the following function by starting with the graph of the function f of x equal to e to the power of x. Indicate the domain, range, x and y intercept, and the asymptote. So we're going to start with y is equal to e to the power of x. Anybody remember how to graph y is equal to e to the power of x, I hope. You can just simply substitute some numbers for x and then get the shape of the graph. Just for the few, if x is equal to 0, anything to the power of 0 is equal to 1, that would be e to the power of 0, which is equal to 1. If x is equal to 1, y would be equal to e to the power of 1, which is just e, and so on. Now, once I look at the graph of y is equal to e to the power of x, you notice that my graph would shift 1 unit to which side, right or left? This is like e to the power of x minus minus 1. So minus 1 would be moving to the left 1 unit. And this minus 3 would indicate that my graph going to shift down 3 units. So this number here would tells me my graph going to shift down 3 units. This minus 3. This right here is really is x minus minus 1. So that means my graph shift to the left 1 unit. Which graph? The graph of y is equal to e to the power of x. Let's take a look at the graph here. So graph of y is equal to e to the power of x. You can see it in blue. And the asymptote here would be the line that lies on x-axis, which is y is equal to 0. The graph of y is equal to e to the power of x plus 1. Would be the same graph of y is equal to e to the power of x, except it would shift to the left 1 unit, and the minus 3 would shift the whole thing down 3 units. So that would move my asymptote down to the horizontal asymptote y is equal to minus 3. From y is equal to 0, my asymptote moved down to y is equal to negative 3. As you can see, the domain would be from negative infinity to positive infinity still. And the range, however, this should be range, would be from negative 3 to the infinity. So this would be the range. And the y-intercept would be when x is equal to 0. If I let x equal to 0, y would be equal to e to the power of 0 plus 1 would be just e minus 3. It's just a number, e minus 3. This is where your graph going to intercept y-axis. For x-intercept, you let y be equal to 0 and solve for x. And then, as you can see, get e to the power of x plus 3 equal to 3. then x plus 1, you have to take a natural log of both sides here, would be x plus 1 is equal to natural log of 3. So x would be equal to natural log of 3 minus 1. So this would be your y-intercept. So let's do that calculation here. Make sure everybody can follow that. If y is equal to 0, you have y is equal to e to the power of x plus 1 minus 3. If y is equal to 0, you want to solve for x, because 0 is equal to e to the power of x plus 1 minus 3. So if I add 3 to both sides of the equation, 3 is equal to e to the power of x plus 1. Because the variable you're solving for is at the exponents, I need to take a natural log of both sides. Natural log of 3 then would be equal to natural log of e to the power of x plus 1. You recall when the base matches this base here, the whole thing would be just simply x plus 1 here to the right hand side, which is equal to natural log of 3. So x would be equal to natural log of 3 minus 1. And that's what we have here. So my x-intercept then would be equal to natural log of 3 minus 1, comma 0. And here, if I have natural log of e to the power of x, that would be equal to x. That's what we're using, because exponent is e. So this x plus 1 just simply move to the next step here. Here we want to graph f of x equal to natural log of x minus 1 using the graph of f of x equal to natural log of x. So I'm going to start with y is equal to natural log of x. You all should know what the graph of this look like. And from here, we want to find the graph of y is equal to natural log of x minus 1. Looks like it's the same exact graph, except you're shifting this 1 unit to the right. That's all we're doing. Let's take a look at the graph. So if this is the graph of natural log of x, if I shifted 1 to the right, that would be the graph of natural log of x minus 1. And the x-intercept would be 2, 0 instead of 1, 0. And the domain would be from 1 to infinity. And the vertical asymptotes move to x is equal to 1. And as you can see, this very similar to the graph of natural log of x. It's like exact graph, we're just shifting this to the right 1 unit. Given x is equal to 5k times natural log of kz minus 1, we're going to solve for z. To solve this, we have x equal to 5k natural log of kz minus 1, and we want to isolate z here. So let's go ahead and divide both sides by 5k first. So first step is to divide both sides by 5k. So I get x over 5k is equal to natural log of kz minus 1. You notice that the base here is e. Then natural log of x is equal to y. I can write this as is exponential form. The base is e. So it would be e to the power of y is equal to x. So that's what we have to do here to isolate z here. So I would write this as e to the power of x over 5k is equal to kz minus 1. Now I can solve for z here. To solve for z, I have to add 1 to both sides of the equation. I get e to the power of x over 5k plus 1. That's the same as k times z. Now to solve for z, I need to divide both sides by the coefficient of z, which is k, and here it is. Z is equal to e to the power of x over 5k plus 1 over k. Given a is equal to this expression, we want to solve for k. So we want to isolate k here. So the first step is to subtract capital T0 from both sides of the equation. So we get a minus capital T0 equal to c times e to the power of minus kt. We're going to solve for k here. I can go ahead and divide both sides by c. So I get a minus capital T0 over c is equal to e to the power of minus kt. Because the variable that you're solving for happen to be the exponents, you need to take a natural log of both sides. So if I take a natural log of both sides, if you recall, if I have natural log of e to the power of x, if that's equal to y, if the exponents, if you recall, natural log of e to the power of x would be equal to x because the base is matching the e. That's exactly what we're doing here. And that's why we're taking a natural log of both sides, so we can bring this variable that you're solving for up front so we can solve for it. So this whole thing, your x would be minus k times t. On the right hand side, we only have minus k times t. On the left hand side, we have natural log of a minus capital T0 over c. So now I can solve for k by dividing both sides by the coefficient of k, which is minus t. So here we have it. K then would be equal to natural log of a minus capital T0 over c divided by minus t. I can put divided by t here and put this minus right front of here, or I can move the minus right to the top of the fraction. All those would be equivalent. So we can take this minus here, leave it right here if you want. You can take this minus here, leave it up there, or just leave it right here. Here we're going to solve. We have log of 16 square over 2 to the power of minus 3. This is my argument, is equal to x, and my base is 1 over 4. We need to write this as an exponential function. Recall log of x equal to y. You can write this as the base b to the power of x is equal to y. My base is 1 over 4. So we're going to write this as 1 over 4 to the power of x is equal to my argument, which is 16 square over 2 to the power of minus 3. So 1 over 4 to the power of x is equal to 16 square times, I'm going to move the 2 to the top of the fraction, that becomes 2 to the power of plus 3. Now the goal is to make all the base the same. I can write this as 1 over 2 squared to the power of x. Now 16 is 2 to the power of 4. So I'm going to replace 16 with 2 to the power of 4 and raise it to the power of 2. times 2 to the power of 3. I'm going to move this 2 up. That becomes 2 to the power of minus 2 to the power of x equal to, that would be 2 to the power of 2 times 4, 8 times 2 to the power of 3. So I made the base the same as 2. So I get 2 to the power of minus 2x is equal to 2 to the power of, I'm going to add the exponent here, 11. So if a to the power of n is equal to a to the power of m, we can conclude from here that n must be equal to m. So the base are the same, the exponents must be the same. So 2x must be equal to 11. Divide both sides by negative 2. So x would be equal to 11 over minus 2, which is minus 5.5. Here we want to solve. On the left-hand side, we have log of x plus log of 3x minus 13. The right-hand side, I get 1. The first step is to combine the logs using the properties. We call log of x plus log of y is the same as log of x times y with the same base, b, let's say. So in this case, there's no base. It means my base is 10. So I can combine this to log of x times 3x minus 13 equal to 1. So my base is 10. To eliminate that log, I need to rewrite this as its exponential function. If y equal to log of x with the base b, that would be the same as b to the power of y is equal to x. So here would be 10 to the power of 1 is equal to my argument, which is x times 3x minus 13. So remember what we just did. We combined the log on the left-hand side using my property, and then I'm going to write it as exponential functions. This is just a linear equation. We can solve for x. We can distribute. I get 3x to the power of 2 minus 13x equal to 10. I'm going to subtract 10 from both sides of the equation, so let it equal to 0. And here you're going to see if we can factor it. If it's not factorable, you can use quadratic formula. So in this case, I'm going to open 2 parentheses. I'm going to use 3x and x here. So for negative 10, I'm going to use 2 and 5. Middle term would be 2x. Further term would be 15x. Can I make negative 13 out of that? Yes, if minus 15 and plus 2 are there. So that would be 3x plus 2 times x minus 5 equal to 0. So I get 2 solutions. 3x plus 2 equal to 0. 3x is equal to negative 2. So x would be equal to minus 2 over 3. Or x minus 5 is equal to 0. X would be equal to 5. We're going to accept x equal to 5 as my solution. However, the minus we're not going to accept. So x would be equal to 5 is my only solution here. Here we're going to solve for x. Step number 1 is to combine the log on the left-hand side. We call that log of x plus log of y is equal to log of x times y with the same base b. Here the base is 5. I will write this as log of x plus 2 times x minus 2 is equal to 1, and my base is 5. My next step is to write this as an exponential function. So if I have log of x is equal to y with the base b, I can write this as b to the power of y is equal to my argument x. So in this case, my base is 5, would be 5 to the power of 1 is equal to my argument, which is right here. X plus 2 times x minus 2, that's difference of a square. That's the same as x squared minus 4. So it would be the same as x squared minus 4. So now I can solve for x by adding 4 to both sides of the equation. I get x squared is equal to 5 plus 4, which is 9. So x would be equal to plus and minus square root of 9, or plus or minus 3. So x is equal to 3, or x is equal to negative 3. I'm going to accept x equal to 3 as my solution. However, negative doesn't make sense. So my only solution would be 3. Here we're going to solve for x. Looks like I can combine the first two terms here. If I have natural log of x plus natural log of y, I can combine it into natural log of x times y. So here I can write this as natural log of x plus 5 times x minus 1. I can move this natural log of 7 to the right by adding that to both sides of the equation, so the whole thing would be equal to natural log of 7. The reason I'm doing this is because if natural log of x is equal to natural log of y, I can conclude from here that x must be equal to y. So drop the natural log. And that's exactly what I can do here. If natural log of something is equal to natural log of something else, the argument must be the same. So x plus 5 times x minus 1 must be equal to 7 then. Then I can just solve this for x. When I multiply these, I get x squared minus x plus 5x minus 5. I'm going to move the 7 to the left also, so let everything to be equal to 0. So I get x squared plus 4x, and here I get minus 12 equal to 0. You can factor this. If it's not factorable, you can use quadratic formula. Looks like this is factorable. I can use 6 and 2 for 12, and I want to make plus 4 out of that, so it would be plus 6 minus 2. So x plus 6 is equal to 0, x equal to minus 6, or x minus 2 is equal to 0, means x is equal to 2. I'm going to accept 2 as one of my answer. I'm not going to include negative as a part of the final answer, so x would be equal to 2 is the solution. Find the exact solution and an approximation of 4 decimals for this equation. We're going to solve for x. The variable that you're solving for, x, appears at the exponents. We cannot make the base the same in this case. The base here is 3, the other one is 7. We cannot make it the same. When you cannot make the base the same, you want to take a log of both sides. I'm going to take a log of left-hand side and also take a log of right-hand side. We're going to use some of the properties that we learned before. One property that we had, if I have log of x to the power of n, that was a power rule. I can move the exponents right in front of the log. And I can do that here. This 2x would go right in front of this log, so it would be 2x times log of 3. If you're trying to solve for x, I need to move the x up front here. So next one, I can do the same. I can bring x minus 1 right in front of log of 7. Now log of 7 is just a number. You can put in our calculator to find what that is. To solve for x, I need to distribute this. So I have 2x log of 3 on the left-hand side. Right-hand side, I have x log of 7 minus log of 7. Remember, we're solving for x. I need to move all the terms that contains x in one side of the equation. So I'm going to move x log of 7 to the left by subtracting that from both sides of the equation, and then solve for x. To solve for x, I need to factor the x out. So it would be x times 2 log of 3. Again, 2 log of 3 is a number. Minus log of 7 also is a number. We use our calculator to evaluate these. Equal to minus log of 7. Now I'm isolating x, as you can see. My coefficient of x would be what I have inside this parentheses. Again, this is just a number. Divide both sides by this coefficient. 2 log of 3 minus log of 7. And we're almost done. That would be my x. So I can write my final answer, x is equal to minus log of 7 over 2 log of 3 minus log of 7. This is the exact solution for x. Now, in order to find the approximate solution, I need to use my calculator. You can grab your calculator and evaluate what log of 7 is. Log of 3 is times 2 minus log of 7. And if you do this correctly, the approximate would be minus 7.7429. Here we're going to solve for x. I have 27 to the power of 4x equal to 9 to the power of x plus 1. The first thing you want to look for is if you can make the base the same. If you can make the base the same, we'll do that. If not, we have to take a natural log or log of both sides. So it looks like 27 can be written as 3 to the power of 3. And then the whole thing should be raised to the power of 4x. Right-hand side, I can write 9 as 3 to the power of 2. The whole thing should raise to the power of x plus 1. So in this case, I can make the base the same. Here I have 3 to the power of 3 times 4, which would be 12x, is equal to 3 to the power of 2 times x plus 1. When a to the power of n is equal to a to the power of m, you can conclude from here that n must be the same as m. So I can write here 12x then must be equal to 2 times x plus 1. And distribute the 2, you get 2x plus 2 is equal to 12x. To solve for x, I can subtract 2x from both sides of the equation, combine like terms. 10x is equal to 2. Divide both sides by 10. So x would be equal to 2 over 10, which is equal to 1 over 5. Here we're going to solve for x. I have 3 over 5 to the power of 2x minus 1 is equal to 25 over 9 to the power of x. If I can make the base the same, I would do that. If I can't, then I need to take a log of both sides. So it looks like on the right-hand side, I have 25 can be written as 5 squared, and I can write 9 as 3 squared, whole thing to the power of x. The left-hand side, it looks like is reciprocal there. So I can write this as 3 over 5 to the power of 2x minus 1. All right, I need to move this 5 to the bottom of the fraction and 3 to the top of the fraction to match the base. I can do that by writing as 3 to the power of minus 2. When I move that to the top of the fraction, the exponents become its opposite exponents, and this would becomes 5 to the power of minus 2, whole thing to the power of x. We're getting a lot closer to have the same base. Looks like on the left-hand side, I have 3 over 5 as my base. On the right-hand side, I have 3 over 5 to the power of minus 2, and then to the power of x. There we have it. We have the base the same. So we can conclude that the exponents must be the same. 2x minus 1 must be equal to negative 2x then. So if I add 2x to both sides of the equation and add 1 to both sides of the equation, I get 4x is equal to 1. So x would be equal to 1 over 4. Here we're going to solve for x. We have log of 1 over 64. This is my argument, is equal to minus 1 over 6. And my base here is x. So I need to write this as an exponential. If you recall, if I have log of x is equal to y with the base b, I can write this as b to the power of y is equal to x. That's what we need to do to eliminate the log. So it would be x to the power of minus 1 over 6 is equal to 1 over 64. And that is my argument here. Now I need to see if I can make the base the same as each other. I can write this as, nope, there's no base here. So in this case, I need to eliminate minus 1 over 6. So raise both of the equation to the power of minus 6 over 1. So I can isolate x. So x would be then equal to 1 over 64 to the power of minus 6, which is equal to 64 to the power of minus 1. If I move this to the top of the fraction to the power of minus 6, so it would be equal to 64 to the power of 6. Now, 64 is 2 to the power of 6. To the power of 6, you could write it as the whole thing as 2 to the power of 36. That's one way to write it. Here we're going to solve for x. The exponents that the variable that you're solving for appear at the exponents, and we cannot make the base the same. We cannot make the base the same. So I need to take a natural log of both sides. The natural log of e to the power of 3x minus 4 is equal to natural log of 1. You recall natural log of e to the power of x would be equal to just x. The left-hand side would be 3x minus 4. What's natural log of 1? Natural log of 1 would be e to the power of x to the power of 1. So x must be equal to 0. Anything to the power of 0 is equal to 1. So natural log of 1 is equal to 0. You could use your calculator for this part too. So you get 3x is equal to 4.